All right. Well, I'd like to thank our sponsors for tonight's program, Friends of Jackson County Conservation and the Jackson County Energy District for sponsoring. So we're really excited to have those two organizations kind of be part of this. And renewable energy really has been a topic of late here at our conservation office, as well as with our Friends group, as we're in the process of raising money for a solar array to power the Hurstville Interpretive Center, which is the building shown there on your screen. So just north of Maquoketa, Iowa, it's the offices for the Conservation Department as well as an interpretive center for the public. And so we're pretty excited about this project. We launched a fundraising campaign last fall, and just the community has really been very supportive of this project. So we're super excited. And if anyone would like to make a donation toward the project, any donations made tonight for tonight's program, we'll just put that right towards this solar project. So thank you, and thank you to our Friends group for helping us with that project. We hope to install the solar array this summer. So look for that, summer 2021. Also with us tonight, we have Bruce Fisher, and Bruce is both a board member for the Friends of Jackson County Conservation and the Jackson County Energy District. And he was the one who sort of lined up this program tonight. And so I just want to thank Bruce, and we really appreciate his work for both of these wonderful organizations here in our community. So Bruce, I'm going to pass it over to you. And if you want to go ahead and introduce our speaker and take it from here.
Thank you, Jess. Welcome everyone for our presentation this evening. We're just delighted to have Dr. Alan Wood apply his knowledge to our benefit. So thank you, Dr. Wood. Aaron is an assistant teaching professor with the Department of Geologic and Atmospheric Sciences at Iowa State University. And he teaches popular courses for young scientists and engineers with a particular focus on the environmental and climactic impacts of acquiring and consuming energy resources. He's going to bring that knowledge to bear this evening and also share with us a little bit about the future of our economy as it relates to energy. So please welcome Dr. Wood. Thank you, Aaron.
Thank you, Bruce, for this invitation, and thanks for joining me, everyone, for this talk. I'm going to try to share my screen here. Hopefully there are no technical errors involved. All right. Okay, hopefully everyone can see my slide. What I'm going to do in this presentation is talk about the transition we're currently making as a nation and as a world towards increasing the usage of renewables, primarily for electricity, but for overall energy needs. And we're going to look at projections up into the year 2050. Not my projections, because I can't tell the future, but projections from reliable institutions like the Department of Energy and the Intergovernmental Panel for Climate Change. And we're going to talk about some of the problems or disadvantages of renewables that will have to be solved along the way. So as you might be aware, that we are currently in an energy transition. We are increasing the usage of renewables. We're also increasing the usage of some fossil fuels. And everyone involved in this transition, and I do mean everyone, the entire world, we could agree that we're doing this, making this transition for the sake of sustainability. But where we disagree is what sustainability actually means. And so I can show some definitions here. Sustainability in itself from Webster's dictionary is just the ability to maintain something. That's not too helpful. So I'd rather draw from the United Nations Sustainable Development Program. And they recognize three categories of sustainability. One is environmental, economic is the second one, and social sustainability is the third and final. And they recognize that a system that is fully sustainable has to meet all three categories. So if we're looking at the Venn diagram over here in the right corner, we got to hit, let me get my laser pointer out for you. We got to hit that sweet spot where all three types overlap. So environmental sustainability, very roughly speaking, I've got a lot of information on these slides, and I'm not going to go over all of it, but environmental sustainability simply means that humans operate within the limitations of their physical and natural environments. Economic sustainability is where our behavior or systems produce operational profits that can ensure long-term economic growth. And social sustainability is a system or behavior that provides a good quality of life for current generations and future generations. And that second part is very important. And as we learn more about the environment, energy markets, social justice, what communities need to be successful, have a high quality of life, the more we learn, that this sustainability target is a moving target. It's a complex moving target, meaning that our energy system or energy economy has to constantly evolve to track that target. The projections I'm going to show you come from reliable institutions, as I said before. One set will focus on the United States, and these projections are issued by the Energy Information Administration, or EIA, as part of the Department of Energy. And I'll show information from other Department of Energy laboratories during the talk. But the EIA's job is to collect and analyze and distribute information about energy, impartial information about energy, to policymakers, consumers, etc. So it's a reliable source of information. I'll also show you some projections from the Intergovernmental Panel on Climate Change. This is a group of scientists and energy and climate experts that were put together by the United Nations to provide information on climate policies using state-of-the-art climate science. And so the most important part of their job, I kind of highlighted here in bold, they provide regular assessments of the scientific basis for climate change, its impacts, risks, and options for adapting and mitigating those risks. So we'll look at those projections after the EIA projections. But we can't really plan what the future is going to be like if we don't know where we've been or where we currently are. So let's look at some background information. We'll focus on the United States. And throughout US history, we've made at least two major energy transitions in our energy economy, going from a wood-dominated energy economy here, where that resource is primarily used for heating and cooking, to an energy economy dominated by coal. So we're looking at late 19th century coal miners here. I would never go into a coal mine with an open flame like that, but that's just me. But this transition into an energy economy dominated by coal led to some benefits: industrialization, steam locomotion, among other things. And then we transitioned to an energy economy or system dominated by hydrocarbons, oil and natural gas. And then that again led to benefits such as air travel, among other things. And what we'll see from one transition to another, the economic risks were quite minimal, making these transitions relatively easy to make. And if you don't buy the pictures, we can look at some actual graphical data from the EIA. In blue, we have the proportion of energy consumption from wood. Orange is coal. And then this purple and bluish green color, that corresponds to hydrocarbons. And you can see from this graph that it was a kind of gradual stepwise transition. And the transition we're making into more renewables is also going to be a gradual stepwise transition, but hopefully on the span of a couple of decades. But I digress. In these transitions, I said they're easy to make for multiple reasons, because the major reason is that if we focus on economic sustainability, which has been the primary focus over US history, with passing attention to environmental and social sustainability, these transitions were easy, because the transition from wood to coal to hydrocarbons led from one energy resource to one that's energy superior. For in these resources, if we look at a metric called energy density, which is how much, effectively in this case, how much heat do we get if we burn a certain mass of a resource, we can see that that value increases from wood to coal to oil and natural gas. So for wood, it's about 20 million joules for every kilogram of wood, all the way to natural gas, which is 55 million joules or megajoules for every kilogram of natural gas. On top of that, once the infrastructure was put in place, the prices for these resources were comparable. And so the consumer didn't really hurt very much at all transitioning from wood to coal to oil and natural gas. They were easy to do because the economic risks were low. One of the arguments about transitioning to more renewables is that the economic risks are greater, because there's a potential, and I just say potential, for more unreliable energy systems if we focus more on renewables. But again, that's a focus on economic sustainability that doesn't take a hard look at the social and environmental components of sustainability. Once we incorporate those, we'll see that the economic risks of keeping hydrocarbons could be just as great. So that's where we've been. Where are we right now? My office phone rang. I don't know why. Pardon the interruption. Here's where we are. What we're looking at this pie chart, and everybody loves a pie chart, is the energy consumption in 2019 separated by source of that energy. And it combines transportation, industrial energy, heating, electricity. It's all of the energy. So if you burned wood in your fireplace in the winter of 2019, well, that's factored in right here. And what we see from this pie chart is that 80% of all the energy consumed in the United States in 2019 came from fossil fuels. So petroleum, oil primarily for transportation fuel, natural gas primarily for heating, electricity, and coal primarily for electricity. Nuclear power, again, primarily for electricity, made up about 8% of that total energy consumed, and renewable energy sources listed here made up only about 11%. We do have some information from 2020, at least the first 11 months. We're still cooking the data for December, but we can do a comparison. And some of the trends, some of the values are very similar, but there are long-term trends that appear. I'll discuss those in a second, but there are some outliers due to the pandemic. So I'll draw your attention here to the petroleum percentages, a drop from 37% of the total energy consumed to 35%. And the reason for that is, well, Americans traveled less during the pandemic. We consumed less transportation fuel, and therefore we consumed less crude oil. So that's likely to be an outlier, especially as we hopefully move out of this pandemic and find some new normal. But the other trends in this data set, they're long-term trends, and I'll show you those on another slide. So what I've done on this slide is parsed out transportation energy versus electrical energy by source. And what we have on the top is transportation energy, and clearly petroleum or oil, that's king in this case. The green line represents renewables, biofuels, and a relatively small proportion of the overall energy consumed for transportation came from renewables. Most of it was from oil. So that's diesel, jet fuel, and gasoline. I looked at this data set a little more closely from the EIA to see if there was anything about all electric vehicles. There was data in there, but the amount of energy consumed by all electric vehicles, end use electricity for these vehicles, was so small it wouldn't even appear on our graph. So that's why I have this picture of a black Chevy Malibu. The black color is supposed to draw your attention to, oil's black. And if the Malibu, the size of the Malibu here, represents the amount of energy from crude oil for transportation, well then some of you with better eyesight than me might see a little red speck there above the door handle. That corresponds to the amount of energy used by electric vehicles. So that's actually a picture of a red Tesla scaled down 1,000 times. So it's 1,000 times smaller than the Malibu here, to give you a sense of the amount of energy for all electric vehicles. How do we expand all electric vehicles? It's an infrastructure question. We're given some hope by the Chevy announcement that in 2035, all Chevys will be all electric. So hopefully in the future, the slice of all electric here in this transportation pie will be a little bit larger. But for the rest of this talk, I'm going to focus on electrical generation. So what's happening down here in this line graph is more relevant. In the long-term trend that we see is that natural gas is growing substantially with every year in terms of usage for electricity. Much more modest growth in renewables. And this is primarily from wind and solar. And then there's a nosedive in the usage of coal. And I'm not going to go into the overall history of coal, but there are some important lessons to be learned about coal and why it's currently too expensive for mass generation of electricity. It's because we factored in those environmental costs. And then a slight tangent here, nuclear has been at a plateau for the last several decades, and it's unlikely to grow much more than that. So our electrical needs are going to be primarily met by natural gas and renewables going forward. So what's going to happen in the future? Well, the EIA focuses primarily on the United States, and they make projections based primarily on market forces. And I'll draw your attention to the first graph here. So we got time on the horizontal axis. We've got billions of kilowatt hours of electricity on the vertical axis. And everything to the left of this dashed line corresponds, well, those are direct observations. That's what we've done. Everything to the right of that line, those are projections based on particular scenarios. And we'll focus first on the reference case. And you can think of this as a kind of a business as usual scenario. And what we expect based on the EIA data is that renewables will make up the majority of electrical generation in the United States under business as usual, okay? And I got the numbers here in front of me, so let me read them off to you. 42% of electricity by 2050 will be renewables, and 36% will be from natural gas. So what's that reference case more specifically involve? Well, it holds energy and environmental policies constant from 2020 to 2050. It expects modest growth in the US population and economy. So you can see the numbers down here. The expectation is that the price of oil will increase over time, but the cost of natural gas will actually decrease. And there will be a moderate decrease in the cost of installing and operating renewables, especially wind and solar power. So that's a business as usual, and it's driven by market forces. There's another set of scenarios I want to draw your attention to, and that's the situation where we have a low supply of hydrocarbons or a high supply. And the difference primarily is that there's either less in the ground we can cost effectively remove than we expected, or there's more in the ground that we can actually remove than expected. And we can see that the low versus high supply cases really impact the proportion of electricity generated from renewables. If we have low supply of natural gas, for example, well then renewables will make up, and we'll get the right number here for you, could make up 54% of all of our electrical consumption, while natural gas is going to stay low at around 19%. If we have more hydrocarbons than we expected, the dominance switches, and so that natural gas will make up 48% and renewables 39%. In both scenarios, the amount of renewables for electricity is greater than what it is today. But the idea in terms of finding that sweet spot in sustainability is to maximize renewables. And so we hope for this situation, right? But it is driven by production of hydrocarbons. So I got this spacer slide here just to pause a little bit and think about why that is. It's because in the United States, we've become a major hydrocarbon producer due to the advancement and distribution and deployment of hydraulic fracturing technology. We can produce a lot of hydrocarbons domestically. In the past, we had to import a lot. Imports are declining. In fact, we are a net exporter of hydrocarbons today. We have such a huge supply of natural gas that natural gas prices continue to fall. So any kind of technology, like a natural gas boiler system or an 800 megawatt power plant that uses natural gas, they're really cheap, relatively speaking, because we have so much natural gas. The technology is very affordable. And we'll get back to this in a bit. Under natural geological scenarios, we have low productivity and natural gas, renewables will take off. Keep that in your minds. But those are economic factors. Let's think about the environmental factors and see if they have economic.
Loud. Oh, it probably don't have to be that loud.
I'm sorry? Okay, I'll continue then. One of the environmental impacts we commonly think of for hydrocarbons involves spills. Maybe the Deepwater Horizon disaster comes to mind. And so this has major environmental impact on natural ecosystems. They also impact human beings. If there is an oil spill on land, that affects soil productivity. It affects fisheries if it's in aquatic ecosystems. And the thing is, we still don't know how to effectively clean up oil spills. For the most part, we do these very obvious cleanup procedures that provide good optics. We transport the oil we collect and we burn it somewhere else. But we don't remove all the hydrocarbons in an oil spill cleanup. What we're looking at here is a picture of the gash in the pipeline that led to millions of gallons of crude oil-like product in the Kalamazoo River watershed. We thought we cleaned that up initially, and then we had to dredge the entire river in order to get the remaining hydrocarbons. And then we burned it somewhere else. And the most effective way to ensure to have a foolproof distribution system for hydrocarbons is, well, it's not to have a distribution network for hydrocarbons. And what I mean by that, and I'll give you a statistic from the Department of Energy regarding pipelines. If a pipeline system has an expected lifespan of 50 years, it's going to have at least 100 leaks during that lifespan. Most of those leaks will be small volumes, but it's going to leak due to human error, corrosion, et cetera. And that's built into the budget, that's built into the planning for the pipeline, et cetera. Okay. And so as long as we distribute hydrocarbons, they're going to be spills, and those incur economic costs. Hydraulic fracturing, I mentioned that before, it involves a lot of water. So there are water quality issues involved. We use 5 million gallons of fluid to create artificial cracks in the subsurface to produce natural gas, oil, et cetera. And almost all this stuff comes back up to the surface. Some what we call formation water comes up too. And that water, that fluid is very salty. It has naturally radioactive material in it. There's a wastewater problem. In fact, there are water issues at every stage of the fracking water cycle. But the big one is wastewater. What do we do with it? We can recycle it, but if we recycle it, we typically use it to produce more hydrocarbons. So that's a problem. We could dispose of it in deep wells, but that in a lot of cases induces earthquakes, so man-made earthquakes, and that's a problem in itself. These problems incur economic costs. That should go into our risk assessment. All fossil fuels, when we burn them, they produce air pollution. And the most problematic, from my perspective, is the particulate matter. So small particles suspended in air. And they're organized by size classes. So PM10 is 2.5 to 10 microns in diameter. Those are some more visible particles. So the brown cloud here, pictured over Hong Kong, that's just a cloud of particulate matter from burning fossil fuels. The slow and silent killer out of particulate matter is this PM 2.5. And this is, of course, regulated by the EPA and state regulatory agencies. But it's a problem because we can't really see it. And if we're exposed to it for long periods of time, we experience lung and cardiovascular damage. So emphysema-like symptoms, increased chance of heart attacks, among other things. And the issue, and one of the important issues here, if we talk about social justice, is that low-income families, families in poverty, families of color, minorities, they often live around power plants. They're exposed to this particulate matter more so than the rest of the US population. And so it's not a homogeneous hazard. If I use natural gas for my electricity, I may not be exposed to particulate matter, but someone else is. And that's because of my consumption. There are economic costs that are incurred from these health risks that should be factored in. And then we can pull out the big issue, climate change. The IPCC likes to summarize things, the risks and what they call reasons for concern. And there's a lot of information to unpack from this particular image. It's from a 2018 report regarding why we should try to meet this goal of only 1.5 degrees Celsius warming by the end of the century. Because you can see the color coding here, reason for concern 1, 2, 3, 4, and 5. What we see with the temperature increase as measured in 2006 to 2015, it's about 1 degree Celsius of warming from pre-industrial temperatures. We're already experiencing the effects of climate change. And so the orange color here, or yellowish color here, let me try to remove, there we go. The yellow indicates impacts or risks that are detectable. We can attribute them to climate change. And so systems like coral reefs, glacial environments, they're already impacted. But what might be more important to us as human beings might be a reason for concern number 2, extreme weather events, especially here in Iowa. So we're talking about hurricanes, tornadoes, real weather events that you come and think of, but we're also talking about forest fires, talking about flash floods, among other things. We're already experiencing those impacts of climate change. And if the temperature reaches 1.5 degrees Celsius relative to pre-industrial temperatures, or even higher, we're going to experience greater risks. So red indicates severe impacts. Purple is the highest severity of impacts that may be irreversible. There's no going back. Okay, so we need to meet this climate change goal of 1.5 degrees Celsius. Got some more examples of impacts that we're currently experiencing. One that is of interest to a lot of people is the heat-related mortality, especially in cities. And so that would be down here. We're already experiencing climate change-induced heat deaths, especially in urban areas. That's something we definitely want to avoid. And so we can put some dollar values on this if you like, to feed into that economic sustainability argument that a lot of opposition to renewables likes to impose upon us. If you think about climate change, well, one of the predictions from the US federal government is that, especially the Department of Defense, I think, came up with this particular estimate, is that with climate change, if we don't do anything to mitigate climate change, then the United States might experience a 10% annual drop in US GDP. So billions of dollars lost every year. That's a huge economic risk. Think about cleaning up fossil fuel related disasters. Well, the Deepwater Horizon, the cleanup itself cost about $62 billion. And of course, there are class action lawsuits, et cetera, that still need to be settled. So that cost is going to increase. The Kalamazoo spill that I mentioned before, it's at $1.9 billion and counting. And so these environmental issues and the social issues, they have costs, right? And so we can't just focus on the economic arguments, but a lot of people do. So what do we do to meet this climate change goal of 1.5 degrees Celsius warming? This again is another plot from the IPCC. I'll try to unpack it a little bit for you. But what you need to focus on is this gray horizontal line at 1.5 degrees Celsius. This is our goal. We want to reach this or be below it, right? And this wiggly gray line represents direct observations of global temperatures. Everything over on this side of the graph, those are projections. And you might see this envelope bound by a thick purple line here and here. If we follow a particular set of scenarios of mitigating climate change, by the end of the century, this is the possibility of warming that we may encounter. And so you can see that 1.5 degrees Celsius of warming is right in the middle. So more or less, there's a 50-50 shot of hitting that target or exceeding it. And this purple field corresponds to scenarios where we actually get our act together, where we reduce fossil fuel consumption, we expand renewables, we do a lot of things that may seem a little daunting today. Even if we get our act together, we might exceed 1.5 degrees Celsius of warming based on various climate models, among other things. The blue envelope, so here's the upper bound, here's the lower bound, everything in between, those are possibilities of temperature increase by the end of the century. You can see by the year 2100, there's 1.5 degrees Celsius. So we might reach it, we might overshoot a little bit, but we're not going to significantly overshoot 1.5 degrees Celsius. And this requires a lot of drastic changes. And so we have to try to clear my screen a little bit. In order to meet that goal, it looks like we have to cut our carbon dioxide emissions globally in half by 2030. So that's less than 10 years from now. And we can't consume any fossil fuels by the year 2050. That's very daunting, if you ask me. This is just one of the scenarios, though. This is one of the potential strategies. The IPCC has provided others. And so if we don't want to overshoot 1.5 degrees Celsius, what they say is that we need to make rapid changes within the next 20 years. We need energy demand to grow modestly over the next 30 years. So only a 21% difference between now and 2050, or sorry, 2010 and 2050, or energy demand has to decrease. But what's really relevant for this talk is the proportion of renewables and natural gas used to generate electricity. The IPCC says that renewables have to make up 70 to 85% of our electrical demand. Natural gas can only make up about 8%. And that's if and only if we use carbon capture and sequestration technology. So we burn natural gas at a power plant, and then we capture the carbon dioxide at the power plant before it goes into the atmosphere. Now, compare those numbers to what the EIA said for the US. So the scenarios I presented said that renewables could be 39 to 54% of electrical needs. Maybe that's, according to the IPCC, that might not be good enough. So we have a daunting task in front of us to expand renewables to meet this climate change goal, reduce the risks, et cetera. Can we do that with renewables? And I want to be optimistic and say yes, but there are problems with renewables, both economic, technological, and environmental, that need to be addressed before we can do this wide-scale expansion, or to be addressed along the way. And so let's take a look at those in the time remaining. So a lot of the expansion of renewables is going to come from solar and wind, and less from hydroelectric, conventional hydroelectricity. In the United States, the reason for not expanding hydroelectricity is that we don't have any other watersheds that we can fully develop for hydroelectricity, because all the big rivers have been developed, especially those on the West Coast in the states of Washington, Oregon, and California. If we did have any other watersheds with a high river discharge that could provide a lot of electricity, we may not want to develop those because of the significant environmental impacts, such as what's involved when you flood a river valley, for example. The argument has been made, though, we have a lot of watersheds that are dammed for other reasons, such as the Mississippi River, Ohio, Alabama, and Arkansas rivers, via a series of locks and dams that help, basically navigate the rivers by freighters. What if we could retrofit those locks and dams to produce electricity for us? And so Oak Ridge National Laboratory, they did a simulation. They figured out how much electricity you could actually make, or looked at the electrical capacity if you actually converted those dams into hydroelectric dams. And they focused on 100 locks and dams on the watersheds I already mentioned. And if you retrofitted them for hydroelectricity, you can expand the electrical capacity by 8 gigawatts. So that's 8 billion joules of electricity for every second in an ideal situation. Are we likely to do that? In my opinion, no, because we already have dams like the Grand Coulee Dam that by itself almost has the electrical capacity. So compare 6.8 gigawatts to 8. Furthermore, if we're thinking about economic arguments, that 8 gigawatt capacity can be met by building 10 new natural gas power plants. And if those 10 natural gas power plants will incur 1/5 or 20% of the costs of retrofitting those 100 dams. So if we're focused on economic arguments, expanding hydroelectricity in the United States may not be a good solution. For other countries, yes, but not for the US. Geothermal energy, we could expand that in the United States. The Department of Energy has located several potential geothermal resources that could be utilized. And geothermal is very attractive because the Earth loses heat very slowly, meaning that when we tap into those resources, they're going to provide reliable electrical baseload power. So it's not going to be intermittent like wind. It's just going to be hot year round. And the current installed capacity for geothermal is about 3.3 gigawatts. And so it's not a lot. The development is quite limited. But the Department of Energy says that, hey, if we tap into a large portion of these geothermal resources, we can increase electrical capacity by 60 gigawatts. And that's quite attractive. What's the the hindrance here? What's preventing us from doing so? Well, it's the large upfront costs of basically understanding the resource to make sure that it can actually produce electricity at a utility scale. So the estimates are that for a particular geothermal site, you're going to pay somewhere between $3,000 to $5,000 for every kilowatt of electricity you want to produce. And you can compare that to the $900 per kilowatt for natural gas. The economics are not in favor of geothermal. Why do you spend so much money trying to understand or survey this resource? Well, you got to have three things. You got to have a rock of the right temperature. That rock has to have some sort of fluid nearby, because it's the fluid that actually transports the heat energy to the surface as steam. And that rock has to have the right permeability. Basically, fluids have to flow into it in order to extract the heat, produce steam, etc. And every geothermal resource is different. And so you're going to spend a lot of money studying it, design the power plant before you even start making a single cent on electricity produced. I have some images here, so later during the Q&A, if you want to talk more about geothermal energy, I got these slides prepared for you. So it's going to be wind and solar. We got to expand wind and solar to a huge extent, and we got to address some issues. And you'll commonly see in I'm running out of time, so I'm going to try to pick it up a little bit here. Common opposition to wind energy is what I would refer to as not in my backyard opposition. And based on the political cartoon at the bottom of the slide, you can see my personal opinion about these NIMBY opposition. But people say the wind turbines are too noisy, they're too ugly, they can decrease property values. There's a fear of eminent domain, and I can understand that. I can be sensitive to that. If we think of the environmental impact during the operational life of a wind farm, there's land use change. So we have all these access roads, we have high capacity transmission lines to deliver that electricity. That's a lot of land use change. So it's something that we should be concerned about. But I want to make clear that the lower property values, that's a fear, that's a psychological phenomenon that most people who've studied this call wind farm anticipation stigma. Property values decrease when people hear about wind farm development, but once the wind farm is operational, property values rebound. But we can talk about that later. These aren't the major issues for wind energy. The major issues come from the different aspects of the wind farm life cycle, the construction phase and the decommission stage. So when you build it and when you tear it down. And when you build it, you need materials called rare earth elements. Rare earth elements are not rare. They're actually widespread across the Earth's crust and into the interior, but they're not concentrated. Meaning that there are a few places on the Earth's surface or just underneath the surface where it's concentrated that you can mine it cost effectively. And these rare earth elements are important for many reasons. They're used in a lot of consumer technology, consumer electronics, but from the perspective of wind power, they're useful for producing powerful, lightweight magnets and batteries. So rare earth elements like yttrium, neodymium, dysprosium, I have them in my hybrid C-Max, and there are rare earth elements in every wind turbine in Iowa and across the world, okay? And right now, 80% of rare earth elements are either mined from or processed in China. And so there's a bit of a stranglehold there on the rare earth element supply. And if we're going to advance green technology like wind turbines, we're going to have to expand mining, look for different sources, and we're also going to incur the environmental costs of rare earth elements. And let me show you what I mean by that. So here's a picture of an artificial lake. It's basically a slurry pond in Inner Mongolia of China, an area where a lot of the world's supply of rare earth elements are processed. And it's difficult to process this ore because it's hard to basically separate the different rare earth elements from each other and then concentrate them. To do so, there's a lot of very toxic chemistry involved. You use high acid solutions, and the waste products end up being a muddy slurry that's highly acidic, very salty, very radioactive. And it's kind of has the consistency of wet cement or almost a jello. And what you do with it initially is you let it sit in a pond and wait for the solids to separate. You bury the solids, and then you do something with the wastewater. You either inject it or you try to recycle it for other industrial purposes. And so this artificial lake, Lake Baotou in China, is humongous. It expands 12 square kilometers. It's 12 square kilometers of radioactive sludge that there's no long-term solution for this material. Give you a sense of the size here. If you've seen the Iowa State campus, Lake Baotou is about 6 times the size of the Iowa State campus. It's a very big slurry pond. We have rare earth element resources in the United States. We have one active mine, but we don't process the ore in the United States. The mining company actually sells it to China. The China separates the rare earth elements and then sells them for electronics, among other things. The Department of Defense has provided economic incentives to actually develop rare earth mines and processing in the United States. The processing centers have been proposed in Texas and Colorado. If we start mining and processing rare earth elements at the same scale as China, we're going to have slurry ponds, radioactive slurry ponds that we'll have to deal with, making it very expensive in both an environmental and economic sense. What about the end of life for the wind farm? We've got to think about what to do with the waste products. Until recently, there was no plan for damaged wind turbine blades, for example. They're composite material, they're aluminum, fiberglass, among other things. They're hard to compact. And so they occupied, until very recently, a lot of space in landfills, primarily in Wyoming. And so one of the environmental impacts that imposes economic costs is, well, disposal in landfills. The good news is that General Electric has declared a partnership that will provide a recycling program, primarily using the fiberglass component of the wind turbine blades in concrete production. And so we can reuse this material and we can reduce our landfill usage in association with wind farms. So if we increase our recycling programs on a national scale, this won't be an environmental issue. And we could say the same thing for high capacity battery storage too. There's no way to systematically or systemically recycle batteries in the United States, like the ones in our hybrid vehicles. If we can develop that technology, that system, that's going to reduce that environmental cost. What about solar? Solar has a lot of great things going for it. For example, for wind farm development, you have to have the right weather climate system in which the average annual wind speed has to be about 7 meters per second to have a utility scale wind farm. For a utility scale solar photovoltaic array, you don't have those limitations. The major limitation for solar photovoltaic, utility scale photovoltaics, is the efficiency of the solar panel. Basically, what proportion of solar radiation can be converted to electricity, and the installation costs. That allows us, those constraints allow us to develop solar photovoltaic anywhere. And so what we're looking at here is a map of potential electrical production from solar panels in the United States. And you can see based on the colors bar here that, yeah, in the American Southwest, great potential, lower potential in the upper Midwest, but the values here, they all vary within 1 order of magnitude. I mean, there's not a 10-fold difference, there's not a 100-fold difference. They're pretty comparable, right? And so there's utility scale installations in Canada. So the Sarnia array is positioned right about here. And I lived in Michigan in this area for quite a while. I can tell you it's not always sunny weather. It's quite cloudy most of the year. You can still produce a lot of solar energy in those kind of climates. But of course, the bigger installations are in the American Southwest, such as the Solar Star Array at a latitude of 35 degrees north, where we get a lot of solar radiation incoming. The efficiency problem can be solved with technology. The installation costs are going down. And so the good news is that if you look at the installation costs per kilowatt for solar, it ranges today somewhere between $700 to $1,400. That range spans the installation costs for natural gas. The costs are becoming comparable. The lower cost solar photovoltaic arrays are the more inefficient systems. The more efficient systems cost more money. And the efficiency of a panel depends on the materials that are used to quote unquote dope the semiconductors. And so the way a semiconductor is turned into a panel is by adding impurities. Those impurities create an electric field, and those electric fields combined with the semiconductor can absorb a small portion of the wavelengths or spectrum of solar energy. But if you stack a particular semiconductor with one kind of impurity, with one with a different impurity, et cetera, you keep stacking those panels or those layers, you can absorb a wider range and therefore increase the efficiency. There's a lot of information on this slide that I used for my class, so you can look at it, but you don't need to understand these points to understand what I'm trying to say regarding the efficiency. So different materials increase the efficiency. The problem with solar, the photovoltaic panels, in terms of environmental costs, is the mining involved to get those impurities. And I'll show you on the next slide what I mean by that. So the very inefficient panels that we use boron and phosphorus, you can mine those materials at a relatively low environmental cost and low economic cost, but the advanced solar photovoltaic panels involve materials like gallium arsenide, cadmium selenide. These are heavy metals. Heavy metal mining can be quite detrimental to the environment. There are similar processing problems as what I talked about with rare earth elements. And so if we expand solar photovoltaic in the United States and across the world, we got to expand mining. We expand the environmental impacts of mining. If we can come up with a technology to recycle materials and therefore recycle heavy metals, that decreases mining. If we can come up with a more environmentally friendly process, chemical process for extracting those materials, that's going to decrease the environmental impact. And so technology can help us in this regard. In terms of other environmental impacts, a lot of land use change. There is some amount of carbon debt. The same thing can be said for wind power, but based on the Department of Energy, the payback time for those initial carbon emissions is on the scale of 2 to 4 years. So you build a solar array, after 2 years of operating, producing electricity, your system is effectively carbon neutral. You don't require a lot of time to pay back those emissions. So that's definitely a benefit for solar. So I'll try to wrap it up here. With those pros and cons and problems we have to address, what is the solution? And so I'll bring it back to the EIA scenarios. And what we need, especially to mitigate climate change, is a scenario or a transition that ends up looking something like what's drawn here for the low hydrocarbon supply case. This scenario is based on what's naturally in the ground, something that we can't control. So one of the solutions that I put forward, and a lot of people put forward, is instead of letting this supply case, I'll say, take place in the future naturally, why don't we artificially create a low supply of hydrocarbons? That will increase the cost of using hydrocarbons like natural gas, making renewables more cost effective. We have more economic reasons. When people don't want to pay attention to the environmental reasons, they'll pay attention to the economic reasons. We'll have more economic reasons to expand renewables like wind and solar. And so that's going to require something along the lines of carbon taxes. And also recognizing the cost of reducing emissions, et cetera. And so I said there's an important lesson to learn from coal. Coal became too expensive when we required power plants to capture sulfur emissions, capture coal ash, clean up the wastewater from a coal power plant. All those extra costs made coal more expensive than natural gas. Maybe we should do that artificially for natural gas power plants, increase the costs through policy. And so as an average person, we don't have much control over that besides talking to our representatives, voting, etc. Where we do have a lot of control is at the community level. And so one of the things I tell my students is that if you can afford to invest in clean technology, you should do it. Because I guarantee there are people on this planet who can't afford it. And so we should do our part to help support them and make the world a better place, right? But as a consumer myself, I can't afford to spend the tens of thousands of dollars to put, replace my roof and then put a solar array on top of it. I don't have that money. But community level initiatives like our solar project here in Ames allowed me to participate. So as I could invest $300, buy what they call a solar pack. It's basically a share of our solar array here in Ames. A lot of people did that in Ames. We crowdsourced enough funding to actually construct the array. And as of November 30th of last year, that solar array is operational. And I feel good that I invested in that. We also need to enhance community level education. And so in Ames, we have the Eco Fair. We take students of all ages to wind farms to educate them about wind technology. And that kind of education is important, especially when we look at the community level opposition to renewables that's out there, especially in the Great Plains states and some of the Southwestern states. Some communities will write out ban expansion of renewables, and they'll say it's because they fear the damage to the natural gas industry. Well, hopefully I've convinced you that that shouldn't be our ultimate concern. Our ultimate concern is mitigating climate change, environmental costs, reaching a more sustainable future. So the more that we can educate the common person, the less likely we'll experience this community level opposition. So I think I'm probably out of time already. So I'll stop there and take your questions. And I just want to say thank you for your attention, and hopefully you enjoyed some aspect of this presentation.
Great. Thank you so much, Aaron. That was a wonderful presentation, and we do have a few questions here
Sure.
that we can go through. Some of them came to me. I don't know if some questions came to you as well in the chat box. One question here is when talking about renewables and sustainability, what are the environmental impacts of corn-based ethanol?
Well, I'll frame it this way. Corn-based ethanol, the original idea was it's carbon neutral fuel, because the carbon that's emitted when we burn it is absorbed by the next year's crops. But of course, we have to use farming technology and farming equipment to grow and harvest those crops. And that equipment does release emissions, right? Carbon dioxide. We also have to transport those fuels, either from the farm to the facility that produces ethanol or to distribute the ethanol. And so we have carbon emissions there. So we have to take the full life cycle perspective of corn-based ethanol. It's not carbon neutral. It's low in terms of carbon emissions, but it's not entirely carbon neutral. In terms of air pollution, the use of fertilizers is greater, right, than with natural gas and crude oil. The use of nitrogen fertilizers leads to nitrogen, what's called NOx compounds. That's a type of air pollutant. And at the gas pump, fuels that have biofuels mixed in, they're more volatile. And so you get more emissions at the gas pump there. So that's another case. But what I would be really worried about is something that I've read from the IPCC and other researchers, is that if we want to replace oil as a transportation fuel with biofuels, we need to expand biofuel production on the order of 17 times what we're doing right now. If we do that, and the world continues to get warmer until we help solve this problem, this leads to a 40-fold increase in what is called water stress. Water stress is where humans use more water than the natural system can provide. There's just not enough water to provide to grow enough crops for biofuels. We've got to find some other means to do it. And that's only from the perspective of growing corn and or sugarcane to generate the ethanol for biofuels.
Okay, great. And for everyone, if you have any questions, you can type those in the chat box, and Aaron will help hopefully answer some of these questions. So another question I have here, for the electric generation by 2050, so you had the 3 graphs and then the 2 projections. It was asked why in the 3rd scenario, or why did nuclear drop in the 3rd scenario where hydrocarbon costs are high? So I think, did the nuclear drop in one graph but not the other?
All right. I see what you're, okay. So when natural gas, when we have a high supply of natural gas, the cost per volume is going to be really low. And so I gave you the value, the current value, it's $900 per kilowatt for construction costs. If the supply increases, that installation cost or construction cost is going to go down even farther. And the current plan is, well, we're going to decommission a lot of nuclear power plants going forward. There may be a few that come online to kind of backfill that portion from nuclear power. But if natural gas power plants become even cheaper in the future, the expectation is no utility company is going to invest in nuclear power. And so that decline that you saw is due to older power plants, nuclear power plants being decommissioned and effectively just becoming nuclear waste facilities.
Okay, all right. Yeah, I think that addresses that question. So yeah, a question on renewables. How do you deal with the lack of reliability and constant supply, of solar and wind?
Yeah, so the reliability when the wind blows or when the sun shines, it changes from region to region. But if you look at national scale data, when we are near peak capacity for wind and solar is typically autumn through the end of spring. That's wind, solar, and hydroelectric, those 3 combined. For hydroelectric, it's because we have higher precipitation, therefore there's more water flowing through the rivers. For wind power, for the Midwest, the Great Plains, New England, et cetera, there's more wind during those months. In the summer, the wind speeds are lower. We don't have as much precipitation. Therefore, we see a drop in the capacity for renewables. And so there's a problem there at a longer time scale. Those summer months is where we have the cooling degree days, right? We need the electricity for AC, for example. And currently that capacity is filled in by natural gas and coal. So if we phase out natural gas and coal, what's going to supply that base load? And that's a big problem. That's a technological problem, right? Geothermal can't do it because, well, geothermal is all concentrated on the western side of the country. And so the plan, and I know the IPCC says it's not a great idea, but the plan is to develop effective and cost-effective carbon capture technology and continue to rely on natural gas to provide that base load power. That's a big if though, right? The carbon capture technology has to be deployed at every power plant, and it has to still allow the utility company to make an operational profit.
Okay. Great. Some questions about the solar array there in Ames. Who organized the community effort, and what community partners were involved with that?
So our utility company is a municipal utility company, meaning that the city runs it, right? So we're not working with Mid-American, for example. And so Ames Municipal Utilities, they organized the project. They advertised it to all their utility customers, this $300 power pack investment. I'm not aware of all the different partners that were involved in the planning, but it was organized primarily by our electrical company.
Okay. And is there a financial return for your investment?
There is a slight reduction in our rates when we buy into the power pack. But those, I don't think that we're going to realize those for another year or so. But to me, it doesn't really make a difference. I'm just happy to make the investment.
Yeah, awesome. That's really cool that Ames has had that opportunity. So a question here about geothermal. Would it be a better idea for new housing to developments to use geothermal?
Okay, so I assume that in the context of that question, you're talking about heat exchange for heating your home?
Yeah, I'm guessing that's probably what they're, if they're developing a new home to heat and cool the home.
Okay, so that's a little different than the electrical generation from geothermal that I was talking about, because you're not producing steam in that case. You're running a fluid in the ground below your house. And in the winter, so the temperature of the ground is going to be about 50 degrees no matter what time of year it is, right? So you can exchange the extra heat in your house during the summer with the subsurface, or you can get extra heat from the subsurface in the winter. And there are some, it also depends, the effectiveness of that depends on how easily fluids can actually flow and transport that heat in the subsurface. And so some developments, neighborhood developments, will be positioned above the right subsurface materials. Others will not. So it has to be assessed on a case-by-case basis. Our hydrogeologist in the department says, in Ames, it's not worth investing. The rate of heat exchange will not reduce your electrical or natural gas costs in a noticeable way. But he used to work in Ohio. In Ohio, the subsurface, basically the glacial till below, had the right permeability, right fluid flow properties. And so if you're going to build a housing development in Western Ohio, it would be a good idea to invest in geothermal heat exchange.
Okay, great. All right, kind of just going through here, another question. Since the economic argument is frequently touted in favor of coal, oil, etc., how does the job production capability compare for renewables?
That's a great question. So you probably read the news about pipelines, the Keystone XL pipeline. The construction has been halted. And the argument is, well, you've just killed, X number of jobs, thousands of jobs. Those jobs haven't been realized yet, right? The construction plans required X, a certain number of workers to help in the construction phase, but no one had those jobs yet. The same thing can be said for expanding renewables, right? You need a certain number of engineers, a certain number of construction crews, et cetera, to develop a large utility scale photovoltaic array, right? And so the number of jobs, I don't know the exact difference. If you're asking for how many jobs per kilowatt, I can't give you those numbers. But I would say that if we do expand wind farms, solar, et cetera, at a tremendous scale, the one that's necessary, jobs will be created.
Great. Let's see, trying to sort out some questions and some chat. A question here about fusion energy. Isn't the ultimate renewable that also meets the energy superior aspect of your presentation? Could that be fusion energy?
Yes. And so far, I mean, there are a lot of experiments using fusion reactors. From my understanding, the limiting factor of scaling it up to what a community would need for generating electricity is the heat required to initiate the fusion reaction. And so basically it takes more energy to initiate the fusion reaction than you actually produce from the fusion reactor. That difference, though, has been decreasing over time. And so a lot of the engineers that I've talked to on this subject say that, within a decade or so, we'll likely have a fusion reactor that produces more energy than it requires to initiate that reaction. And that's, if that technology continues to advance at that pace, then by the end of the century, we could potentially have fusion reactors. What are the environmental implications of using those reactors? I'm not sure. There's a lot of excess heat produced, but I'm not quite aware of radioactive materials, what's involved there. But right now, it's just the energy return on investment is, well, it's negative.
Okay, yeah. Okay. All right. One more question. I think that's all. So if I missed your question, I'm kind of scrolling through a lot here. You can submit it again here. But one more question here was just maybe some web pages to get more information. And my thought was I'm going to send out a recording to everybody who registered. So Aaron, maybe some of those like graphs and things, some of those the sources that you kind of are utilizing, maybe you could share those with us or with me, and I can send those out to the group.
Yeah, I can share the presentation. There are a
Okay.
lot of articles and data sources in the hyperlinks. So if
Okay.
you have a PDF of it, just click on that link and you'll go to the source.
Perfect. Yeah, if you want to email that to Bruce or I, and then we can share it with those who register tonight, and that would be great. So some folks asked for just more information. So
Sure.
awesome. Well, Aaron, thank you so much for your time. Very interesting, and I know I learned a lot. So I really appreciate you taking the time to join us this evening. And
Thank you.
yeah, it was really cool, and we're excited for hopefully some community efforts here in Jackson County. And folks have a few more minutes. I'm going to invite Bruce to come on and share a little bit about what our local Jackson County Energy District is doing for a solar group buy here in Jackson County. So thank you again, Aaron, really appreciate that. And yeah, Bruce, do you want to take a minute to share what the Jackson County Energy District is up to?
Will do. Thank you, Jess. And thank you as well, Aaron. Terrific presentation, very informative. And very timely with regard to your experiment in Ames and the community-based solar array that you put together. We have a slightly different approach in Jackson County, but I'm very excited to share it with the attendees today, and that is the Jackson County Grow Solar program that is being initiated as we speak. We're looking to have a very successful group buy where we can all combine our purchasing power and hopefully develop systems that will be both environmentally sound and financially lucrative to us as well. So if you are interested in learning more about the Grow Solar program, which you'd be eligible to participate in as a resident of Jackson County, as a business in Jackson County, or as a farm in Jackson County, please reach out to us at the Energy District. You can either send us an email. I believe it's jacksoncounty.energydistrict at gmail.com, or you could also offer us the opportunity to get on our website, which is jacksoncounty.energydistrict.org. You can see there at the bottom of that slide, I kind of messed up the Gmail address, but reach out to us. We'd be happy to talk with you, and no obligation, but we'd educate you and maybe get you involved in the process. So we're all trying to do our bit here at Jackson County, and we look forward to working with you on it. Thanks, Jess.
Great. Well, thank you, Bruce, and thanks again, Aaron, and thank you everyone for joining us this evening. So have a great night and enjoy this spring weather.
Thanks again, everybody.
Yep. Bye.